Okay, I'm going to continue 4.4 and get on to the more interesting subject of 5, even though there's some graphing in 4.5, which is important. And redo this one because I botched it. Find the constants A, B, C, such as we're giving a cubic. That will have a local extremum, which means the slope here will be 0. And a point of inflection, which means the double derivative will be equal to 0 at that point, and sketch the graph. Okay, let's go with what we know. We know 2 points on the graph. We have 3 variables, so we need 3 equations, and we have 2 points on the graph, so that'll give us 2 equations. And probably either the first derivative or second derivative will give us another equation. So let's look at the first derivative of this graph. Okay, so here's the formula itself. Here's the first derivative, which we may or may not use, except we will use to graph it. First derivative is 3ax squared plus 2bx, and the c doesn't matter. So we have a first derivative formula without a c in it. And then here's the second derivative formula of x is 6ax plus 2b. So we have a second derivative formula. Now, we also happen to know that this second derivative is going to be equal to 0 at this point, because that's what a point of inflection is measured. We also know it's going to be equal to 0 at this point. Now, interestingly enough, both these equations will only give us, will probably give us the same equation, because a derivative is directly related to where it came from. So there's, well, you'll see. So let's start with this point, first point here. We know that this is a maximum or a min. So that means when x is 2 in the first derivative, the result's going to be equal to 0, because the first derivative is equal to 0 at a maximum. So we're going to replace x where we see it with 2. 3 times 2 squared is 4. So it's 3 times 4a, which is 12a. And then plus 2 times b times 2 is plus 4b. And we know that's equal to 0. So if we readjust for b, we get 4b is equal to minus 12a, which means b is equal to minus 3. So there we go. Interestingly enough, if we use the second derivative now, we know at the second derivative, 6ax plus 2b is going to be equal to 0. We also know the second derivative point of inflection is at 1 comma 5, so x is 1. So we get 6a times 1, which is 6a, plus 2b is equal to 0. Now note we get the same equation here. Oh, over here this should be minus 3a. Notice we get the same equation. B is equal to minus 3a. So it's really not that much help to us, except in graphing. So we'll just get rid of that, because we already have b is equal to 3a. What else do we have? Well, we have the original formula. And we know in that original formula, when y is 11, x is 2. So we'll just put that in as the formula. We get 11. And what is x 2 cubed? It's 8. What is 2 squared? It's 4 plus c. So we know that at 11, it's going to be equal to 8a plus 4b plus c. But we also know that when y is 5, x is 1. So we're going to have a times x cubed, which is a, b times x squared, which is b, plus c. So we have another equation with 3 variables that's different from our first equation. We now have 3 equations, one for b here, one for all 3, and one for all 3. So our first step is going to be, wherever I see b here, I'm simply going to put in minus 3a. So I get 5 is equal to a minus 3a plus c, which means that c is equal to 5 plus 2a. So you go ahead and do that. Now I have an explanation for c, and I have an explanation for b, and both have to do with a, which means I can work on this formula right here and come up with my answers that I need. So I'm going to do that. Wherever I see c here, I'm going to put in this formula, and wherever I see b, I'm going to put in this formula. So I'm left with 11 is equal to 8a plus 4 times my new b, which is minus 3a, because you're allowed to use an equation over and over again, And I'm going to put in my new c, which is 5 plus 2a. And I get 11 is equal to 8a minus 12a plus 5 plus 2a. So 8a minus 12a is minus 4a, and 4a plus 2a is minus 2a. So I'm going to get the 2a to the other side, and I get 2a is equal to 5 minus 11. What's 5 minus 11? It is minus 6. So I finally get a is equal to minus 3. So I have my a. If I have my a, I therefore have my b as expressed right here. If b is equal to minus 3a and a is minus 3, then b is equal to 9. If I have my a as well, I have my c from this equation. If c is equal to 5 times plus 2 times a, then c is equal to 5 plus 2 times minus 3, which is minus 6. And 5 plus minus 6 is equal to minus 1, which means I have my equation. And let's not stop there. I now have my c, my b, and my a. Okay? And that means I can fill in my original equation, and I also have my formulas for derivative, but I don't need those yet, which means I can replace this blank equation with this. Minus 3 x cubed plus 9 x squared minus 1. And that tells me a bit more information. It tells me that I have a y-intercept at 0, minus 1. So that means I have several points. I got 0, minus 1 I know is on the graph. I know 2, or 1, comma 5 is on the graph. And I know 2, comma 11 is on the graph. Great. That's a lot of information already. So I'm just going to move this. And I'm going to put this, I don't know, somewhere down there. And I'm just going to expand. There we go. Great. So they're going to ask me to graph it. Now, notice that this cubic should be minus 3x cubed here. I didn't have the minus down properly. So that means it's not starting in quadrant 3 and ending in quadrant 1. It's starting in quadrant 2 and ending in quadrant 4. Since I also know it's going through, since I also know it only has one point of inflection on a cubic, and that point of inflection is 1, comma 5, I know there's a point right there. Since I know there's another point that's either a max or min at 211, I know that point's right there. Since I know it's coming in from here, and I know it goes through 0, minus 1, there's a good chance that this is the graph. So that means that's going to be a maximum, and that's going to be a point of inflection. And it's going to go through the x-axis very close to the y-axis in order to hit this point right here. So I know that this point right here, from my formula, the formula gives me the x-intercept. I also know this is a point of inflection because they told me, and this is a max or min, and I can deduce that it's a max just by the nature. But if I'm not sure, I can put in 2 into the double formula, or the double derivative formula here, where I see x, and I also know a is minus 3 now, so I can rewrite my derivative formula as minus 18x plus 2. And I can also rewrite this one here as minus 9x squared, and b is 9, so plus 18x. Great. My only question is, right here, when x is 2 into this formula, what do I get? I get minus 36 plus 2, which is minus 34, which is essentially a minus, which tells me that point is a maximum. So I've confirmed that that is indeed a maximum. You could not find the x-intercepts by factoring, but you could put it through the quadratic function and come up with all those x-intercepts, but they just wanted you to sketch the graph. So we're coming up with pretty good information. Now you might say, okay, so if this is a max and this is a min, how do you know it doesn't do something else? Well, since there's only one point of inflection, I know the whole graph has to curve until that point and then change directions at that point. That automatically tells me this graph must be shaped like this. The second point is the y-intercept we discovered right there is below the x-axis, which means it has to cross the x-axis before it gets to that point. To get back to the maximum, it must cross the x-axis after that point to come back. So that's how you know it's going to be shaped like this. And sure enough, when we throw it into the graph, that is indeed what we get. You could also do the quadratic function formula and come up with all the... oh, no, you can't for a cubic. Sorry, you could not. You'd have to find a factor to factor out first. And since there's no clean factor, we can't. However, the graphing does show us the x-intercepts clearly. It's exactly as predicted. It has to follow that pattern. It goes up to the max and back down. There, a little less butchered than before. Let's try the next question. And let's see if... Yeah, I didn't want to do 9 because that's all theoretical. I hate those things. But I can do 11, which is one I accidentally glossed over last time. And I botched 12, I remember. So I might as well do 12 clearly this time. There's no point in me doing these if I don't do them clearly. I haven't done this one, so I hope it works out. But since they only give limited information, we must find the constant b, so it's a number, such that the function is equal to this, has a point of inflection here, which means the double derivative of this is going to be equal to 0 when x is 3. Well, that should be enough to solve it. We need to take the first derivative. So the first derivative, let's rewrite the formula the way I like to write it. It's x plus 1 to the half plus b times, if you want, x to the negative 1. So here we go. And that's a half, which means I have to do the chain rule in the first one and then multiply it times the content. Now, fortunately, the derivative of the content. So I'm going to just focus on the first part. The derivative of the first part is 1/2 times x plus 1 to the negative half times the derivative of x, which is just 1. So fortunately, I'm just left with that, which means I have the wonderful, and I'll just rewrite it. If I'm going to rewrite it in their terms, it's going to be this. It's just this. But I'm going to keep it in this term over here. If I take the chain rule here, I just treat it like a, I treat b like a number, and I get minus b to the x to the minus 2. And that's the chain rule there, which would be written like this. Minus b over x squared. So if I needed to, write it or present it more clearly, that's what the first derivative would look like. Okay? But I'm not. I'm going to leave it in the... I'm going to leave a little shrinked version of this over here, but I don't think I'll need it. Now I'm going to take the second derivative. So I'm going to leave it in this structure because it's easier for me to take the second derivative. This comes down in front. I get negative 1/4 in front. And then I get x plus 1, and I have to lower that negative half by 1. So that's negative 3 over 2. Then I have to take the derivative of the next one, which is plus 2b, which is what happens when you multiply minus 2 times minus b, x to the minus 3. So there you go. Now, if I'm going to rewrite that in normal terms, as I did above, and I'm just going to move it to the right. You get minus 1 over 4. And what does that 3 over 2 mean? It means the square root of x plus 1, just like that. All to the power of 3. That's what the negative 3 means. All to the power of 3. And you have to put it under like a bracket. I'll just kind of bring it down a bit. There we go, like a fraction. And then the second one means I have plus 2 times b all over x cubed. all over x cubed. And that's the second derivative written in a more easy to see term. They're both, this is equal to that, and this is equal to that, but this is just written like a fraction, and this is just written like a single line formula. They both work, except this is easier to do when we now know that if this is the second derivative, if that's the second derivative, we know that a point inflection occurs when the second derivative is equal to 0. So this whole thing is going to be equal to 0. And it's going to be equal to 0 when x is 3, which means I can put x in there. And I can put x3 is in there. So I get this. I get minus 1 over 4. And what's 3 plus 1 in that square root bracket? It's square root of 4, which is times 2 to the power of 3. That's all that means, because the square root of 4 is 3. So what do I get here? I get this. What is 2 to the power of 3? It's 8. What's 8 times 4? 1632. So I get negative 1 over 32. Boom. I have a number. That's great. This 2b, I just leave it like it. And it's all over x cubed. Well, I happen to know that x cubed is equal to 3 there. So it's all over 27. Is equal to 0. Now, before I can add those, I'd have to find a number in common. But the easiest thing for me to do is cross multiply. So when I cross multiply, I just don't have to worry about the 0. I get minus 27 plus 64b all over 32 times 27. Now, I actually don't have to multiply this out, but I will, just for you. And all I did there was figure out a common denominator by cross-multiplying. What does cross-multiply mean? It means I have to multiply 27 times this numerator, 32 times this numerator, and then have to multiply the denominators. Now it's all equal to 0. Now why didn't I have to figure out this bottom number? Because now to get this all alone, I multiply it by 864 over 1 to make this side disappear, and I have to multiply it on this side as well, but it becomes 0. That's why I didn't even have to bother figuring it out. So I'm left with this is equal to 0. Now it's quite clear that really, if I get the b's on the same side, if I did all my numbers right, I get 64 is equal to 27, or b is equal to 27 divided by 64. I believe they can both be divided by 3, so I get 9. No. Can they both be divided by, I forget if 64 cannot be divided by 9. Stupid. So I believe I just get the fraction 27 over 64. Now, I might have made some calculation errors, but let's see. I'm going to open a new, I remember I had the answer somewhere, and I'm going to open 4.4, and we're dealing with, yeah, there we go, 27 over 64. And I'll also pull up number, there we go. Let's just pull up this. There. 27 over 64. I got it. So they picked a really weird one just to be annoying. Keep in mind that this represents b, just this top part, not x. So it'd be 27 over 64 over x, which would be the same as 27 over 64x if I was to replace this entire fraction. Okay, also please note that we got the question number 10 correct as well, right there. I just forgot to check it. A is indeed minus 3, B is 9, and C is minus 1, and there's the graph. But we didn't need to do that because of Desmos. I don't know if I'll be able to do 12, but I will give it my all, and by that I mean barely try. Okay, let's see. show that this has 2 points of inflection, or prove that it has 2 points of inflection. And that means that the double derivative would have to equal 0, and I'd have to have 2 solutions. But I also have to show that the x-coordinate of one of these points lies midway between the x-intercepts, which means I should be able to discover the x-intercepts. What do you notice about this formula? What do you notice about this formula? Let me just move it up a bit and shrink it just a little bit. Well, it has x cubed in it twice, doesn't it? Which means I could take out x cubed, and I'd be left with ax plus b, which means one of the intercepts is indeed 0, 0. And the other intercept, when I make ax plus b solve it, I get minus b over a, comma 0. And that's just taking the original formula and factoring it. So this, of course, is 0. And this, for it to equal to 0, would have to be minus b over a. And how do you solve that? You just make this, you know that it hits the x-intercept when this bracket is equal to 0. So you make it equal to 0, and you solve for x, and you get this, minus b over a. Okay. So that means I have 2 of the x-intercepts. I know that one as 0, 0, and the other one is at a mysterious spot, minus b over a. Okay, well that doesn't tell me too much, does it? But let's take the derivative of the first derivative. So you get 4x cubed plus 3bx squared. That's the first derivative of the formula. And then when you take the second derivative, which is where points of inflections are of interest, you get 4ax squared plus 6bx is equal to your second derivative. And I got to remember to put the squared here. Great, so now we have the second derivative. Now, according to this, they're asking us to prove 2 points of inflection. Well, that's when the second derivative is equal to 0. So the question is, can we factor that and prove that there's 2 points of inflection? Well, yeah, I can take a 6 out, and I can take an x out, and I'm left with 2ax plus b is equal to, let me make sure I got that right, is equal to 0. Which means there's 1 point of inflection, that's 0, 0. And there's another point of inflection when 2ax plus b is equal to 0. Well, that's when 2ax is equal to minus b. And that's when x is equal to minus b divided by 2a. So that means the second point of inflection exists here. Let me rewrite that to make it more clear. That's the same as minus a half, or if you want, a half, which is even more clear, a half, when I take a half out, of minus b, hate when they don't quite line up, minus b over a. That's when I factor out a half. So I can see it's a half. And why did I do that? Well, because already up here I discovered one of the points is minus b over a, and that this point of inflection occurs at half of minus b over a, which is what the question asks. Show that the x-coordinate of one of these points of inflection lies midway between the x-intercepts, which is between 0 and minus b over a, and the halfway point of that is half of the distance. So how do you find half the distance between 2 points? You add them together, which becomes minus b over a, and you divide them by 2, which becomes minus b over 2a. Boom. That's the halfway point, which was the point of inflection right there. A little cleaner, I think. 3. Ugh. Sketch this function. So, let's do it by as much factoring as possible. There's obviously a trick to this, otherwise question B wouldn't exist. Does the top have a factor? Yeah. we can take x out, and we're left with x squared minus 2x plus 4 up top, right? And then does that have a factor? Yeah, it's x minus 2, is it? Yeah, and x plus 2, which I believe is the case. Is it? No, it's not. Let me see if it has a factor. Is there a number multiplied that adds up to 2? No. Minus 4 and minus 1? Nope. Minus 2 and minus 2? Nope. So there's not. Interesting. Is there a difference of cubes going on up top? No. Huh. There's something tricky here. Anyway, at the bottom, if we factor it, we get x plus 2 and x minus 2. All right. Now, it's saying how that'll help us determine a couple things. It'll help us determine the x-intercepts. So I would take a quadratic function, figure out that. And I know one of the x-intercepts is 0, 0. So right away, I can start by graphing this and saying, well, we're dealing with a cubic here. It goes through 0, 0 for sure. Okay. And then I can say it also has a horizontal asymptote here and here when x is 2 and minus 2. Now, I know that it's going to have an oblique asymptote because this is one higher than this. So if I take, and I'm just going to take this and put this over here somewhere. If I take the top and divide long division style by the bottom, I get x here, and x times x squared is x cubed, minus 4x squared. And when I subtract them, I get 0 there, and here I get minus 6x squared plus, no, when I subtract that, I get 2x squared, sorry, minus 4x. And then I bring the 4x down. To get to that next one, and this is all you need, is plus 2, which means the line, the horizontal asymptote, is going to be equal to this. X plus 2. It's going to go through the y-axis there, which means you're going to have some weird thing going on. It's probably going to do stuff like that. It's probably going to do stuff like, it's going to hug the asymptote. And when you look at it, x cubed divided by x squared, it's sort of a line that gets interrupted twice. It's going to do this. It's probably going to go down and then hug here. It's probably going to go up and hug here and then go down and then go up. And then it's probably going to do some weird thing on this side. So you would have to measure on each side of this. It would also help to figure out the x-intercept. For instance, I know it goes through here at one point. It also helped to see if it crosses the asymptote line, which you should mark down as well. And this one's actually really complicated because we're doing a whole bunch of things here. So you got y is equal to x plus 2 as the oblique asymptote. So far, so good. You will also want to see if this ever equals, so you take the original one, ever equals your asymptote. In other words, does it ever cross it? when I bring the other one up, I get x cubed, or x squared minus 4 times x plus 4. So I get x cubed plus 2x squared minus 4x plus 2, like that. It's essentially multiplying by the denominator here to get rid of it. And when I subtract the 3x cubed, it disappears. When I subtract this, it doesn't disappear, which makes me think I should be very careful and make sure I got the right one. X cubed plus 2x, so minus 2x. No, it disappears. So I get x cubed, got it, plus 2x squared, got it. So it doesn't disappear. Okay, so I got the right thing. Minus 4x, got it, plus 2. So yeah, I did get it. So when I get it to the other side, the x cubes disappeared. The x squareds become minus 4x squared. The 4x becomes plus 8x. And it becomes minus 2 is equal to 0. Which means it's going to cross the asymptote twice. And when I take minus 2 out, I get 2x squared minus 4x plus 1. I'm looking for minus, is it minus 2 minus 2? X minus 2. So a number that adds up, no, it won't work. Minus 2 minus 1 doesn't work, which means I would have to take the quadratic function of this to see where it's crossing the asymptote, but it does indeed cross it. So it might be worth it to figure that out. So I'm going to take 2x squared minus 4x plus 1, and I'm going to do a quadratic function calculator. And I happen to like this one. And I'm going to take those numbers, 4 plus 8 minus 1. Oh, no, those aren't the numbers. It's 2, 4, and 1. 2 minus 4 and 1. I hit calculate. And I'm going to discover it's going to cross the asymptote at these points. Great, and I can even graph it, so that means it's going to cross. When I plug in this into the asymptote formula, that's where it's going to cross, and when I plug this in. So it's going to cross it at 2 points, somewhere over here and somewhere over here. Okay, great. And it's one's on the, are they both on the positive side? Looks like they're both positive. Yeah, they're both positive. So one over here and one over here. So it's doing something weird. Now, what else can we learn? We can take the derivative of this one to see what other x-intercepts are there. So I get 1, minus 2, and 4. And it looks like we're dealing with an imaginary number for 1. Yeah, they're both imaginary. So there's no solutions. See? 2 imaginary solutions for this. X squared minus 2x plus 4. Which means it only crosses once. So it's going to do something weird like that, and something weird like that, and it's going to hug the asymptotes. It's weird that I came up with 2 solutions over here for crossing it, which means maybe I did it wrong, but we'll just ignore that. So what you would do now to sketch this is don't assume what I've drawn is correct. So we're just going to try to get rid of some of the drawing. Okay. What you would actually do is say, okay, it only crosses the x-intercept once, so that helps. So you have to set up your table. You have to set up a table, and you have to figure out what does this graph do at, let's say, minus infinity. And then you say, what does it do just on the left side of minus 2? What does it do between minus 2 and 0? What does it do between 0 and 2? What does it do just on the other side of plus 2? And what does it do on plus infinity? Okay. And for plus infinity, this technique they use, and I'm going to get rid of the drawing for now, even though, you know, I shouldn't. Actually, you know what I'm going to do? I'm going to shrink this, and I'm just going to bring the drawing further down for now. And then I'm going to come back to that. Okay. One thing they do for this formula to figure out what it's going to do for plus infinity is they say, we're going to take, essentially we're going to divide everything at the top by x cubed. We're going to take x cubed out of it. Well, let's take x squared out of it. If I took x, what's a good way to think of it? If I have positive infinity up here, I'm going to get positive infinity cubed. If I have positive infinity at the bottom, I'm going to get positive infinity squared, which comes out to just positive infinity at the top, which means that our graph on this side, as we go towards infinity, will go up here, which means we're dealing with something like this. Okay? Because we know way over here, positive infinity, it's doing that. All we need to know is what happens when we're right at like 2.01. Okay? Or 3 might do it. So that helps. We're way up in positive infinity. We also know that when we're way up at negative infinity, the top becomes negative infinity cubed. And it stays in negative because it's cubed. But it becomes positive infinity squared because when it comes squared. When we cancel out, we're left with negative infinity, which tells me way off negative infinity is going to go way down here. So we're dealing with something that comes up and then hugs. We're dealing with something that comes down and then hugs. And it might even come down on the right side and then cross and hug. Or it might hug and then cross, and hug and then cross. Really just depends where it crosses, and I could just use a calculator and test to see if it crosses the x-intercepts or not. You should also see that's all you need to see. Now you take your factors and you put them on the left. So you got an x. You got this whole mess here. And it would help if I had a bit more room, but that's okay. I'm just going to instead try it again. And then I'm going to move this over here like that. And I'm going to put this as a factor. And then I'm going to put this as a factor. And they all go down as factors, especially if there was a number there. Like that. And then you're going to put all your rules at the top, like that. And you're going to draw boxes for all the rules. And you should also have a box at the bottom that says the result, positive, negative, or where it ends up. So you should also have a box down here for the result. Okay, and let's try this. When this is negative infinity, I can just sort of say it's negative. I can say it's positive. I can say it's negative. And I can say it's negative. And I can see that it's going to come out as negative. When this is just to the left of minus 2, let's say minus 3, I get 9 plus 6, 15 plus 9. So that's going to be positive. I can see that the x is going to be negative. I can see that here minus 3 plus 2 is going to be negative. And minus 3 minus 2 is negative. Which means I'm still on the negative when I'm on the left side of the x-axis. So that's good to know. Maybe it crosses. It's also good to notice that there's going to be a local max, so she figure out the local max with the derivatives. But for now, that's good to know. What's a good number between x and minus 2 and 0? It's minus 1. So this is going to become 1 plus 2, so that's 3, plus 4, so that's going to become positive. It's clear that this x is going to be negative. It's clear that this is going to be negative 1 plus 2 is going to be positive, and negative 1 minus 2 is going to be negative. So we get negative times a positive times a positive times a negative. We get a positive. So that means between the 0 and this, it's going to be above the graph like that and cross over. Now, we should make sure, but it's almost certain that it's going to climb way up high. So if you had the formula in a calculator, you would put like minus 0.201 and positive 2.01 to make sure it climbs to positive infinity to negative infinity. But I'm almost certain this is what it's doing. Then you continue with your box and you say, what's a good number between 0 and 2? Well, it's 1. So you get positive on the x here. It becomes 1 minus 2, so that's minus 1 plus 4 becomes positive. 1 plus 2 is positive, and then 1 minus 2 becomes negative. So the whole thing becomes negative, which just confirms for me that when it goes through 0, 0, it's now on the negative side in here. So it's going to hug like that. Now, the local max and mins are of interest to me, though. So now we just go above 2. We're going to take 3. So we hit 9 minus 4, which is 5, plus 4 is positive. And we can see just x is going to be positive. And then 2 plus 2 is going to be positive. And then this is going to be negative. So that's interesting. It is not up here after all. It's down here. So it's going to climb up like that and then hug, which is not what I thought it was going to do. So it's going to be way down here, and then it's kind of going to come up to the horizontal asymptote, but it's either going to cross it, which I believe we found out it probably does cross here, and probably does, yeah, and then does cross here, right? So it's going to cross somewhere there and go up. So there's going to be 2 crossing points which we could determine. And then finally, you should probably determine if there's a local max, because this might come out and or a local max there. You should probably find the derivative of it. Now, I might just use the formula to find the derivative of it, because the derivative of this thing is going to take a long time. So, yeah, I could sit around and find if there's a local max and min, or I can just let Desmos do it for me for now. But if I was going to find if there's a max or a min, I'd take the first derivative, then I'd take a second derivative, make it equal to 0. Or sorry, take the first derivative, make it equal to 0, and see if it's solvable. It wouldn't be too bad finding the first derivative. It'd just take a long time. So I'm going to just take Symbolab instead. And I'm going to ask it to find the derivative. And yeah, they really want you to practice this, but this is such an exceptional question that I don't know if I'm going to spend that much time doing it. And all of it divided by x squared minus 4. And let's make sure I got it right and take the first derivative. So they've simplified the first derivative, and you can see it would have been quite complicated. And I'll just go down here and make a copy. This is the first derivative here. So you would have had to make that equal to 0. You would have had to see if there's any factors out of it. So that would become this. And you could see how hard it is to see if there's any factors that involved here. You'd have to take synthetic division and see if 1 is a factor, minus 16, plus 16, minus 16. It'd be very difficult. So instead, I'm going to just ask Desmos to graph this for me. Maybe it'll copy it for me too. I don't know. And it did. It does indeed have a local max and min. I got what happens to it on this side incorrect, which makes sense. It should reflect. However, a lot of what I predicted is correct. I'm going to draw the line y is equal to x plus 2. I got the... oh no, I got it. I got the oblique asymptote correct. I got the crossing points for the oblique asymptote correct. I probably should have figured out the first derivative. So if I make this equal to f of x, and I take the first derivative, and I set it equal to 0, it will give me the max and min points. So, I mean, it's pretty hard to solve the first derivative of a cubic. You'd have to sit around, since there's no pure factors, you wouldn't be able to come up with a nice answer. I think the book is just going to show us a drawing, which is always a pain, instead of explaining. Yeah, they just did it here. They're not really implying that there's a way to find the max min points. You'd have to just plug in some points and come close. The only thing I'm bothered about is that I came up with the wrong measure over here. So, looking back at my number for it, when I plugged in over here, I shouldn't have got negative values. So let's try it again. Something above 2 is 3. So 3 is positive. 3 here is 9. Minus 6 plus 4. So that's positive. 3 plus 2. Oh, this one is not negative. It's positive. So that's where I screwed it up. Yeah, if I take an x squared out of both sides, I'd be left with x minus 2 plus 4 over x on the top, and just 1 minus 4 over x squared on the bottom. And I could see that as x reaches infinity, when these cancel out, that it just become infinity over 1. Positive infinity. So it just tells me it would reach infinity. There's really no reason to do it like that. Came pretty close to guessing what was going to happen. Notice that when there is an oblique asymptote, it tends to go down below it and then start climbing up. I'm really upset that I got that part wrong, but I should have known better. The rest looks pretty good. All right. Graphing takes a long time. Can be a pain in the butt. Find the inflection points if any exist for this graph. No, I'm not going to bother. So that's it for that. Not really useful. A little bit, not too much.